Hello, this is FlippedHarber for Precalculus. In this video we're going to talk about 3D vectors. Our objectives for this lesson are to find the distance between 2 points in 3D space, find position vectors in 3D, perform vector operations in 3D, find the dot product of 3D vectors, find the angle between two 3D vectors, and find the direction angles of a 3D vector. Now, a lot of this is going to seem very, very familiar. We're just adding a third dimension. The idea of the direction angles, that's going to look a little bit different than what we've seen, but still pretty easy. The outline for this video, we'll start by just taking a look at what 3D space is. We'll take a look at a 3D vector and how to write 3D vectors. We'll look at the distance formula in 3D space. We'll look at our vector operations again in 3D. We'll take a look at the dot product in 3D. We'll talk about how our properties of the dot product work. We'll take a look at the angle between vectors in 3D. We'll take a look at direction vectors. We'll take a look at a theorem about the properties of direction cosines. And finally, we'll take a look at 3D vectors in magnitude and direction form. Now, 3D space is exactly what it sounds like. It's the three-dimensional x, y, z space that we basically live in. So this might look a little bit funny, the fact that x is coming out at you, but this is how we draw 3D space typically. Z is straight up and down, y goes left and right, and x is coming out of the paper at you, or out of the screen at you right now. Now, a 3D vector is made up of three component vectors. Instead of just I and j, now we have I, j, and k. So we would say that this blue vector v is ai plus b times j plus c times k. Now a is the distance along the x-axis. So again, that's the distance out of the paper or out of the screen towards you. B is a distance in the y direction, and then C is the distance straight up parallel to the z-axis. Now you might remember these dotted lines from a previous class, from Algebra 2. You had to draw these three things to describe a point in 3D space, so really this should look somewhat familiar. Now our distance formula in 3D space actually looks a lot like our distance formula in 2D space. It's still a square root. We're still adding up some things that are squared, but instead of just the square root of a squared plus b squared, we now add in c squared. So again, you could think of this as the three-dimensional Pythagorean theorem. So the distance from 2 points is equal to the movement along the x squared plus the movement along the y squared plus the movement along the z squared, and then you take the square root of that whole sum. Pretty straightforward. Now all of our vector operations in 3D behave just like they would in 2D. We can still add and subtract vectors. We do the same thing. We add the a values, that is the coefficient in front of the I unit vector. We add the b values. We add the c values. If we're taking the difference, we subtract them. We can do a scalar multiple, putting the scalar alpha in front of v. You just multiply each component by alpha. Our magnitude, again, looks very familiar. The magnitude of v is equal to this distance formula that we just saw. A square root of a squared plus b squared plus c squared. The dot product in 3 dimensions also should look very familiar. We still take the a components, multiply them together. We take the b components, we multiply those together, and you probably could have guessed that we take our c components and multiply those together, and then we add them all up. So really we just take our dot product from 2 dimensions and we add in this third dimension. So everything is behaving very, very predictably. All of the properties that we learned about the dot product still hold true. The dot product is commutative. u dot v is equal to v dot u. The dot product in 3D space is still distributive. When you take a vector and dot it by itself, you still get the magnitude squared. And when you take a zero vector, dot it with a vector, you still get the number 0. So notice again, that first 0 has a bar over it. It's a 0 vector, which is 0i plus 0j plus 0k, since we're in 3D space. But when you dot it times any vector, you get just the number 0. The angle between two vectors in three-dimensional space looks exactly like the equation that we had for the angle between vectors in 2D space. The only difference is it's going to take us a little bit more time to find that dot product. It's going to take us a little bit more time to find those two magnitudes. But again, everything is behaving pretty much the way we would expect. Now, direction vectors, or really direction angles, this is a little bit hard to picture for some people. So I'm going to try to draw a vector here. Now this vector is pointing out into space. Now if this is a little bit hard for you to picture, that's okay, that's understandable. I'm going to try to help you out a little bit by drawing a box. Okay, so I'm going to create a box using the x, y, z axes. So this is our x-axis, this is our y-axis, and this is our z-axis. Now I'm going to try to draw a box here to help you visualize this, that this vector is pointing kind of up, out, and to the right. Okay, so I don't have the best artistic skills, but I'm going to give it a shot here. What I'm going to do here is drop a vertical, and now I'm drawing a line parallel to the x-axis and parallel to the y-axis, and it's down on what appears to be the floor. It's actually the xy plane. I'm going to draw a vertical line right here. This is in the xz plane. Now it looks a little bit tall, but you got to realize that it's back away from us a little bit. Now I'll connect here. I'll connect here. I'm going to draw a couple more lines. There we go. So I've drawn this box to try to accent the idea that this vector is pointing out towards you, up, and kind of to the right. Now our direction angles that we need to talk about are angles between each axis and the vector that we see on the screen. So there is an angle between the vector and the x-axis. That is angle alpha. There is an angle between the vector and the y-axis. That is angle beta. And then of course there is an angle between the z-axis and our vector, and we're going to use the Greek letter gamma. Now these are all lowercase, so that's angles alpha, beta, and gamma. Now we have a theorem that relates these three angles together using the cosine. So it says simply that the cosine squared of alpha plus the cosine squared of beta plus the cosine squared of gamma has to equal 1. So the cosine squared of each angle, when you add them all up, you should always get 1. Now, looking at our magnitude direction form in three-dimensional space, we see again this cosine alpha, cosine beta, and cosine gamma. And we use those just like we did in two-dimensional space, except notice that they're all cosine. Not cosine for one of them, sine for another one. They are all cosine values now. Okay, because we're not just always referencing to the x-axis, they've each got their own angle back to their respective axes. So that's why they are all cosine. So this is probably the biggest change that we see in this section, is that all of these are cosine values instead of some of them being cosine and some of them being sine. Okay, you know what? If you've been paying attention in the bottom left-hand corner, this is our last slide. So I will see you in class, and I'll see you online.